Good morning, everybody. So it is often said by advocates of ZK rollup technology that ZK is the end game. I'm going to argue today that that is not the case. Now, you might think I'm going to argue this because although ZK arguably is capable of proving the execution of legacy chains at the speed and cost that we see on legacy chains, that it is not capable of proving the next generation of very high throughput, more sophisticated chains with features like Arbitrum stylus. I'm not going to make that argument today. For the purposes of this talk, we'll assume that ZK technology is able to operate at the speed and at the cost required by next generation platforms. I'm going to argue that even if that is the case, nonetheless, optimistic plus ZK is the end game. In other words, that a hybrid protocol makes sense even in a world where ZK proving is cheap enough and fast enough to routinely prove the execution of high-end chains. So in order to get there, I want to start with a bit of level setting by talking in a little bit more detail about how L2 chains, state-of-the-art L2 chains operate today. And I'll use the design of Arbitrum for this, but other state-of-the-art L2s are typically pretty similar. So you can view the design as consisting of these four components: sequencing, execution, data management, and proving. And I'll talk in a minute about what each of them does. But what's important about this is that these four components operate separately and asynchronously from each other. They interact through well-defined APIs with well-defined expectations of behavior, but they really do operate as separate components, separate subprotocols, if you will, that fit together in order to make the full L2 protocol. So let me talk about what each of these does. The first step is sequencing. And in a well-designed L2, the sequencer has one and only one job, and that is to put transactions into order, to recognize the transactions that have arrived from users, and to establish and publish a list of those transactions in the order in which they're deemed to have arrived. Now, you can have different mechanisms for deciding on the ordering. That might be a different talk. But for today, let's just assume that the job of the sequencer is to record the transactions that have arrived in whatever is the canonical order. And that's its only job. It's not trusted for anything else in a well-designed L2. Now, the output of the sequencer goes to two different components. First, you have the execution layer. The job of the execution layer is to take the transactions that are produced by the sequencer and to build blocks from them, to execute them, to discard any that are invalid because the sequencer is not trusted to filter out invalid transactions. It's incented to, but not trusted to. The execution layer computes the blocks. And it does this according to a deterministic execution rule so that any node can do this independently. The other thing that happens with the result of sequencing is to record that sequence of transactions by writing it to the L1 chain in a way that is optimized, typically by aggregating and compressing. And then, finally, you have proving. The role of the prover is to prove the blocks. That is, to prove which blocks are the correct outcome of executing the transactions that were recorded by the data management. And we're talking here today about the prover. Okay, let me review a bit about how optimistic proving works. The first thing to understand is about assertions. So an assertion is a claim that's made by some L2 validator. And an assertion contains, as you see here, it contains an L2 block height. It contains an L2 block hash or claimed block hash, which the asserter claims is correct. And it has a status, which is either confirmed, meaning the protocol has decided that this is correct, and final, and that it's fully correct, or pending, meaning the protocol has not yet decided whether this assertion is correct, or else rejected, meaning the protocol has, well, rejected it. And you have this chain of assertions like this, each having a predecessor that points to an earlier block height. Okay, now the common case in optimistic proving is a situation like this. Here over on the right, we have Alice, who is staked on some assertion out at the end of this chain. Over on the left, we have a a few of the assertions that are fully confirmed, and then we have a whole chain of assertions, each pointing to its predecessor, and at the end of this chain, we have Alice staked. So this is the common case, and roughly once per hour on Arbitrum, Alice will add another assertion to the end of this chain, and roughly once per hour, another one of these yellows will turn green as the protocol confirms it. That's the common case. Now, the other thing that can happen is something like this, where Alice and Bob make different competing claims, inconsistent claims about the state of the chain, and Alice and Bob are each staked on these. When this happens, there's a dispute protocol. And I'm not going to talk today about the dispute protocol. I'm going to go deep dive on the latest Arbitrum dispute protocol at the SBC conference tomorrow morning. But for now, just all you need to know is that the optimistic protocol will identify one of these claims as the correct one, and you can think of that dispute protocol as basically being a fork choice rule. Okay, now, let's compare this kind of optimistic protocol against ZK protocols. An optimistic protocol relies on some assumptions. It relies on the assumption that the parent chain is safe and live. That parent chain, it would be Ethereum for Arbitrum 1, and also that censorship on the parent chain is bounded. That is, the amount of censorship that can happen within a limited period is bounded. The optimistic protocol also assumes that there's at least one active and honest validator in the protocol, and this is required for both safety and liveness of the protocol. ZK also relies on assumptions that it assumes that the parent chain is safe and live, and it also assumes that there's at least one active, honest, and well-resourced prover for liveness. So this is an assumption for liveness, not for safety, but it does require that in addition to being active and honest, that this party is well-resourced. So let me take a minute and talk about this well-resourced requirement because it's important in thinking about the practical implications of these protocols. The reason that we need a proving node to be well-resourced is that we want to be able to run the chain at full speed. And full speed means the maximum execution speed of an ordinary node. So we want ordinary users to be able to execute the chain at speed so they can run a full node. And we want our chain to go as fast as possible. That means that an ordinary node is going to be maxed out by executing the chain if we're doing this right. Proving an execution takes longer than just executing it. The ZK community is working really hard on reducing the disadvantage, the ratio of proving to execution time, but it's still very significant. And what this means is that you need more resources to prove the chain than an ordinary node has available. And this tends to centralize the proving function in ZK rollups. And that is a disadvantage because we would like to be able to make a stronger guarantee about decentralization. ZK gives faster confirmation. Optimistic, on the other hand, lets an ordinary node acting by itself guarantee liveness and safety without requiring extra resources. So there's a trade-off here between ZK and optimistic. Okay. One more thing to note here is the question of what happens if there's a bug in the prover. In both cases, but especially in ZK proving, there's an awful lot of complexity in the prover. What if a prover bug allows a bad result to be confirmed? Now, prover bugs, we hope they don't exist, and all teams spend a lot of diligence trying to prevent it, but we can't rule it out. If we were an L1 chain, then we could do a social hard fork. That is, we could, by social consensus, decide that the history that we thought was correct or that some software thought was correct is not actually the correct history. A social hard fork can, in effect, either freeze or roll back the chain if something goes wrong, and that happens by social coordination of people deciding to upgrade their software because it's ultimately a social consensus deciding which chain history is correct. On the L2, we don't have that option. Because L2s confirm and settle via smart contracts to the L1, an L2 must follow the execution of its contracts on L1. So we don't have the option of a social hard fork. So we need to take some kind of preventive action on the L1 parent chain as an on-chain L1 action in order to cope with the prover bug. And in practice, L2 chains will tend to have some function like a security council, which is some kind of multisig that can intervene in case of a prover bug. Now, on Arbitrum 1 and Arbitrum Nova, the Security Council is a set of publicly known parties who are elected by the Arbitrum DAO. I think that's the best practice for having a Security Council. But I think in practice, on an L2, you want to have some kind of Security Council that can, at the very least, pause the chain and trigger a sort of social recovery phase if something goes wrong. So major L2s have some form or another of this. In fact, in ZK provers, the common approach on ZK rollup chains is that when a ZK proof is presented, the protocol typically allows some kind of grace period. And the grace period is basically a period of time, it might be a day, for example, that the Security Council has to veto the proof, to say even though this proof checks out, even though it passes the cryptographic verification code that's on the L1, we, the Security Council, think that the claim that is allegedly, that's being made here was allegedly proven is actually incorrect. Note that this is a hybrid ZK optimistic protocol. You have a ZK proof, but following it, you have an optimistic period in which you're waiting for, let's say, a day, for some parties to act in order to undo the protocol. So the first point I want to make, the first major point is that today, ZK rollups tend to actually use a hybrid protocol and to do it for good security reasons. That is, that they need the ability to recover from a security, from a prover bug. And I'll note that optimistic rollups don't have to worry so much about this because they already have delays that are built into their protocol. And so if something seems to be going wrong, the Security Council already has time to recover. Okay, but if ZK rollups are using a hybrid protocol already, let me suggest that there is a better hybrid protocol that combines elements of ZK and optimistic proving. And that protocol, I would argue, is this. First, let's start with the optimistic protocol as I described above, where parties make assertions. Those assertions are held as pending for some length of time. If no one disputes them, they're accepted. If someone makes a conflicting claim so that the assertion chain forks, we have a dispute protocol. Let's start with all of that. And then let's add two operations to the protocol. Operation number one is that you can ZK prove one of these assertions. That is, you can ZK prove that, assuming its predecessor assertion is correct, that this assertion is also the correct next assertion. And when you do this, the protocol will simply mark that assertion as ZK proven. It won't confirm it immediately because we might not know whether the predecessor is actually going to be confirmed. Then we'll also allow a separate second operation which allows us to instantly confirm an assertion if two things are true, if that assertion has been ZK proven and if its predecessor has been confirmed. So if we do this, then we have a protocol where you can ZK prove if you want, but you don't have to. So let me talk about how ZK proving would play into each of these two use cases that I showed you before. The top one is the kind of ordinary case of an optimistic protocol where we have Alice who is making a long chain of assertions. So in this case, Alice, if she wanted, could, when she posted each of these assertions, could accompany it with the ZK proof. That would allow Alice to then immediately confirm each of these assertions and turn each one green at the moment it was posted. Alternatively, Alice could post these, and someone else could follow along behind her, maybe close behind, ZK proving each of those assertions. Now, in a well-designed optimistic protocol, the next assertion that will be made is deterministically knowable. And so, in fact, if someone other than Alice is doing these proofs, they can get started right away as soon as the previous assertion is posted. Down in the bottom here, where we have the other use case where Alice and Bob are disagreeing, we could, in this case, the optimistic protocol would start a dispute, a multi-round dispute protocol. But alternatively, either Alice or Bob or anyone else can just ZK prove that one of the successors at the fork point is correct. And that would allow the dispute to be resolved immediately by ZK proof. Right? So we have the option of either optimistic proving, but anyone can jump in and ZK prove something whenever they want in order to move the protocol ahead faster. So the details, logically, there are now 3 separate operations on an assertion. You can propose it, you can ZK prove it, or you can confirm it. And you can confirm it if it's been either ZK proven or it's confirmable according to the optimistic rule, and also its predecessor has been confirmed. So the use cases here, well, one use case is where someone proposes, ZK proves, and confirms the next assertion all in a single transaction. That behaves like a ZK rollup protocol, at least while this is happening. Alternatively, you can propose optimistically and ZK prove it shortly after. Or alternatively, you can just use the optimistic protocol routinely, but if there is an optimistic dispute, you can just shortcut the multi-round dispute protocol by ZK proving one of the branches directly. And then if you like, you can either ZK prove everything else in the chain or just resolve that dispute by ZK proof, if that's the way you want to go. So this protocol gives a lot of flexibility. How do you deal with prover bugs? Well, one way to do this is to adopt the kind of grace period mechanism you want, but you can do a little bit better. We can require a ZK proof to come along with signatures from a majority of some confirmation committee. And those confirmation committee members are attesting that they have checked the assertion themselves by execution, and they agree that what is being proven is correct. And then the combination, then basically the protocol ignores a ZK proof unless it carries signatures of a quorum of this confirmation committee. So this gives you some security against a false assertion being ZK provable. And by the way, the optimistic fallback also gives you security against a situation where nothing is provable because of some other bug. A situation where a pure ZK protocol would need to use Security Council intervention. So the protocol will then naturally fall back to optimistic proving if this committee is not live, or if a ZK bug prevents proving of a valid assertion, or if nobody generates a ZK proof at all. All right, let's talk about the economics of ZK proving, because we know ZK proving is more expensive than optimistic proving. Optimistic proving costs 0. In the common case, you don't have to do the dispute protocol. And if you do the dispute protocol, because of a loser pays rule, we can put the entire cost of the dispute onto the malicious party whose fault it is. So, but if we're doing ZK proving, you have to actually generate the proof every time, and that's going to carry a cost. That's one of the arguments against always ZK proving. So the chain is going to, one way or another, need to collect revenue to support the cost of ZK proving. This will either increase chain fees, or else it will divert revenue from the chain owner, which might be a DAO, or in the case of an app chain, the app developer. Either way, that money needs to come from somewhere. So a good approach here is that chain governance, whether that's a DAO or an app chain owner, can decide how much it's willing to spend on proving, and then it can just offer a bounty for ZK proofs, however much it's willing to pay. If someone is able to prove for that amount, great, they'll collect the bounty, and the ZK proof will happen. If ZK proving is more expensive, turns out to be more expensive than that, or if the chain doesn't have an amount, perhaps the chain is offering a fraction of its gas fees for ZK proving. If the chain doesn't have enough traffic to generate enough revenue to support ZK proving, no problem. ZK proving won't happen. You'll continue in the optimistic mode. The idea here is just to let the economics take care of itself. The chain can offer a bounty which is equal to how much the chain values ZK proving. And then ZK proving will happen and will be in equilibrium if and only if it can be done at a cost that the chain is willing to pay. Okay. So I would argue that this kind of hybrid protocol gives you the best of both worlds between ZK and optimistic proving. Again, assuming that ZK proving is at the performance and cost that you need for a state-of-the-art next-gen chain. So you get ZK proving in the common case, if and when it's actually worth what the chain is willing to pay for it. If not, you fall back to optimistic. The chain will run at the speed of execution. That is, you can run at the speed that an ordinary node can execute the chain rather than having to slow down to the speed of ordinary node proving. And it's still the case that any ordinary node, without special cost or without special equipment, can enforce safety and liveness, because an ordinary node can make optimistic assertions and can participate fully in the optimistic protocol, even if they don't have the resources to ZK prove. So I would claim that the end game is optimistic plus ZK, and that optimistic plus ZK is better than ZK. Thanks very much.